All right, guys, here's a problem that has us calculate oxidation numbers based on structures. Now, there's two ways to calculate oxidation numbers. One of them is to apply a hierarchical set of rules. Now, that works as long as you have all the atoms in the structure, but you do have to kind of deal with the entire structure and all of the atoms as a whole to then pinpoint any one particular atom. So let's take a look. There's a different way to do it too, and it's similar to the calculation of a formal charge. If our formal charge calculation in a Lewis structure was to take the number of valence electrons from the periodic table of elements based on the column that atom is in and subtract from it the number of valence electrons that we assign in the structure. Now, for formal charge, we assign those electrons evenly so that we just split them. A single bond, one electron goes to one atom, the other electron to the other atom, and the same thing with a double bond. 2 to 1 and 2 to the other. Same thing with a triple bond, 3 to 1, 3 to the other. The oxidation number assignment is different, and that's all that's different in calculating oxidation numbers. It's just the assignment. In this case, we're going to assign them based on electronegativity. So the atom that is more electronegative will get assigned all of the electrons. The atom that is less electronegative will get assigned none of the electrons. The only exception to that rule is, of course, if they're the same atom, then we'll just go back to assigning them evenly. One to the atom on the left, one to the atom on the right, or up and down, whatever the direction of the structure may be. This is a much more elegant way to calculate oxidation numbers because you don't have to deal with the entire structure. But what you do need is you do need a Lewis structure in order to understand the bonding. So let's take a look at how we're going to calculate these oxidation numbers. Let's look at this first structure. So the oxidation number is going to be based on the number of electrons from the periodic table of elements. And for carbon, that's 4. And then let's do the assignments. For the carbon-carbon bond, I'm going to assign 1 to each atom because they're the same atoms. So the same thing goes here. Now, I can't forget that there is a carbon-hydrogen bond. And for carbon, it's more electronegative than the hydrogen. So I'm going to assign them both electrons. For the oxygen carbon bond, the oxygen is more electronegative. So I'm going to assign all of the electrons to oxygen. So now let's count up the electrons that we assigned to the carbon. It's 4. So 4 minus 4 equals 0. So the oxidation number of that carbon is 0. Okay, let's take a look at the next structure. It seems like I've got 2 bonds to oxygen this time. So let's calculate the oxidation number. I expect it to be higher. So it's 4 minus the assignment. Now, again, like before, the electrons in the carbon-oxygen bond will be assigned to oxygen. The electrons in the carbon-carbon bonds will be split evenly because they're the same atom. Let's look at the electrons that I assigned to the carbon. Looks like I've only assigned 2 in this case. So 4 minus 2 equals positive 2. And that makes sense. More bonds to oxygen, larger electron number, more positive electron number. Okay, so here we have a carbon that has even more bonds to oxygen. So we should expect that the oxidation number is even higher still. And so let's take a look at the assignments. All of the bonds from the carbon are to the oxygens. So I'm going to assign them all to the oxygen. And that means that I end up assigning none of them to the carbon. And so I end up with an oxidation number of plus 4. And that makes sense because this structure has even more bonds to oxygen. All right, let's take a look at this structure. Now, this structure has 2 bonds to carbon and 2 bonds to oxygen. Well, so did this structure. 2 bonds to carbon, 2 bonds to oxygen. So what we expect is that the oxidation number should calculate to plus 2. Let's see if that's the case. Oxidation number equals 4 minus, let's do the assignments. 1, 2 evenly, 1, 2 evenly, and then all 4 to the oxygen. I've assigned 2 electrons to the carbon, so it's 4 minus 2. That equals plus 2. And so indeed, I did get the same oxidation number. All right, so let's take a look at this structure. But the only difference is here, remember, I've got 2 bonds to hydrogen. So I need to assign 1, 2 there, 1, 2 there. We'll split the carbon-carbon bonds. And now let's count how many we assigned. It looks like I assigned 1, 2, 3, 4, 5, 6. So the oxidation number is 4 from the periodic table minus the 6 that were assigned. So the oxidation number is minus 2. That carbon is clearly more reduced than the other carbon, so we expect the oxidation number to be more negative. Let's take a look at this guy here. All right, so now I have 3 bonds to oxygen. So if this one with 2 bonds to oxygen is plus 2, and this one with 4 bonds to oxygen is plus 4, maybe we would have a logical deduction that says maybe this one will end up being plus 3. Let's check it out. 4 minus, let's do the assignment. 1 will go to the carbon that's asterisk due to the carbon-carbon bond. All of these electrons will go to oxygen. All of these electrons will go to oxygen there. I've assigned it 1 electron from the structure. So 4 minus 1 is plus 3. And so there you have it. There's all 6 oxidation numbers.